So I think we should continue with our afternoon session. The next speaker is Shuai Lu from Fudan University of Shanghai. So he's probably well known to all of you, and he for scientific work on inverse problems. So just a few words. He got his PhD thesis during his stay at a long-term stay at University of Linz in Austria, and now he's back in Shanghai at Fudan University. He's a full professor there since 2015. So the title of the talk is on parameter identification in linear stochastic differential equations by Gaussian statistics. So please go ahead.
Prato. So first I would like to thank Ben and Antonia for kindly having me here. And I should confess, yesterday was the longest day in my life because I fly from Shanghai to here and it take 23 hours in the plane. So I mean, not say in the flight, but in the plane. So I take 9 hours from Shanghai to Dubai and another 14 hours from Dubai to here. But it's really worth it to come here, and I enjoy it very much. My name is Shuai Lu, and currently I'm with Fudan University in Shanghai. And today I try to report some ongoing work, which is not finished yet. And we start to think about this problem in 2011. But only this year, we try to understand this problem a little bit more. And we have some preliminary result, and I try to report here. And maybe I would really appreciate if you have some comments and or suggestion to improve it. And it is a joint work with a PhD student in our group, Ms. Pingping Yu, who is now in Helsinki visiting Professor Marty Lassas and Tapio Helling for half year, and also our group leader, Professor Jing Chen, in Fudan University. So this is outline of my talk. I first introduce to explain why I interested in the linear stochastic differential equation and what is the motivation, and also the existing result. And I should say that the existing result was really poor, that I only have 3 kind of different methods that we can use currently. And we were starting from the very simple Uhlenstein-Uhlenbach process, which is with all these parameters are constant. Then we will move to the Langevin equation to tell people that we can do further by Gaussian statistics to recognize or identify some parameters in the linear stochastic differential equation. And of course, inspired by the so-called data assimilation, we really want to say that what happens if we have indirect observation, which is very natural in inverse problem. And also some conclusion will close my talk today. So the ambitious or the motivation that I try to do is such kind of parameter identification of stochastic partial differential equation. For instance, like you have a diffusion equation here, and now you have several constant parameters like C here, D here, mu here. We assume that all of them was constant. But the different thing that I try to do here is that you have a random source here, which means that your source has certain mean here, fx times ht, depending on space and time. And also you have Brown emotion here, which tells you that you are now dealing with a random equation. And for this kind of randomness or stochastic background, people are really now focused on this kind of problem. And I think that the UQ, quantity uncertainty quantification, has become a very popular topic in applied mathematics now. And I try to see that what is behind this, or especially from inverse problem viewpoint. So the direct problem was doing this. So give me the parameters of C, D, mu, and also all these functions here. Can you calculate the random field of Vxt? And what people was doing is always like you build up some prior. Then in this case, you can generate so-called Kuchel-Leuven expansion, which coming from the approximation theory that you generate an eigenvalue system for your prior. Then you can generate randomness to obtain the random field of Vxt. And of course, here, this is just one dimensional. You can extend it high dimensional if you like. The inverse problem was like this. Can you recover the function of fx and gx? I assume that you have only spatial unknowns, because otherwise you have big problem if this ht was unknown. So I just assume that the ht was known to me. Then can you identify this function of fx and gx from the measurement Vxt that you can have from t larger than t0? Well, this kind of partial differential equation or stochastic partial differential equation was always hard to solve. So we will say that what happens if we reduce such kind of problem back to frequency domain. For instance, like you take a very simple 2-pi periodic solution. Then in this case, you can generate the Fourier series. In this way, by taking the frequency number of k squared, you transfer the original stochastic partial differential equation back to frequency domain that you have the sequence of stochastic ODEs. Then in this case, the unknown of this fx and gx, you assume that, of course, it's periodic. Then in this case, you just need to find out the constant of fk and gk in your unknowns ODEs. And of course, you will have some initial guess, tells you that now you're starting from 0 time, then you proceed further. Starting from this kind of stochastic ODE, we start to think about whether it is possible, say, to identify different parameters in these ODEs. And we will go to the most simple case that all these parameters are constant. For instance, like you have this gamma here, we call it damping constant. Then we have v hat here, which tells us it is the force function. And also the sigma here is like volatility. And I think that most people, especially like Ben, you have working on this recovery of the volatility from some options, and this can be seen as a particular case for this kind of problem. Once again, we have a Brown motion here, and if you assume that your initial state V0 was Gaussian, then because it is a linear equation, then all these states will become Gaussian as t goes to infinity. The forward problem, easy. You just calculate this Vt, giving all these parameters here. You have gamma, V hat, and sigma, as well as the initial state. Then this kind of calculation was following this Ola-Maruyama discretization, and you can calculate easily if you choose the time step very small. The inverse problem was seen this way. If you have the observation of Vt, and I use continuous observation here, which tells you that you know all these flows when t go from 0 to infinity, and of course it may happen that you have discrete observation, which tells you that after different time step, you have the observation. But we will start a very simple one. So can you identify, for instance, gamma, we had sigma here, from the measurement of Vt, and how many measurements you need to identify these 3 parameters? I have to say that I started to have this problem in 2011 when I was participating in the Applied Inverse Problem Conference in Texas, organized by Bill here. I listened to the talk by Peijing Li, and he talked about inverse random source problem, which is also connected with the talk in the morning. Say that you try to identify the source which is random. And I start to think about this kind of problem that I proposed before, since 2011, but only for this year, I found out some solution to solve this problem. That is why the existing result was very few, and I can take all these reference here. For instance, like what happens if you have point-wise observation, which means that you're having starting from time 0 to infinity, then you measure 1 point measurement, and you try to identify all these sources. And we have a sequence of paper by Professor Gang Bao and Peijing Li, and also one of the latest paper by Professor Andrew Stewart from Caltech. And I should say that this paper inspired me quite a lot. On the other hand, we have a similar, say, setting from continuous observation, and you only try to identify the parameter by single pass. And I should mention this kind of work coming from non-parametric estimation of diffusion, and also one of the paper by Professor Thorsten Hahake. They try to penalize by maximum likelihood with respect to these unknowns that appearing in this stochastic differential equation. Now let's go back to what people have done before. So as I mentioned before, we only have 3 techniques to solve such kind of problem. The first one was referenced by Professor Gang Bao and Peijing Li. You have the Helmholtz equation, then you have the source of Gx here and Hx here. Both of them was the deterministic setting. Then you try to identify this G and H from the measurement for U at certain point of X. So the technique that they used was like first order reduction, because you have second order equation, then you go back to the first order, you extended the dimensionality of the problem. This is regular way that people was doing in mathematical method. And in order to identify this G and Hx uniquely, then you have to have firstly multiple wave number, which tells you that the omega should change from 0 to infinity. And secondly, in order to have point-wise measurement, then you have to have multiple boundary data so that the law of large number will tell you the mean and the variance of your solution at this certain point. And this is one of the techniques people was working. So in this case, you have to assume that this omega was known. 1 plus qx was also known to me. These only unknowns was G and H. Secondly, you're dealing with such kind of equation, But this case, the mu was depending on this xt, so this xt becomes nonlinear after a certain time t starting from 0, then you go to nonlinear setting immediately. Then what people was doing like this, assume sigma was known, then you can transfer, say that for a continuous observation, this kind of xt to the density function of Fock-Planck equation, so that this unknown of this mu will appear as a low order term in this diffusion equation. Then what you need to do is using regularization theory to identify this mu here. And of course, you can use your favorite method to build up this mu, since you know that this this u is always a probability measure. So in this case, you can use Kupler-Lever divergence to quantify the difference between different probability density, because the integration was always equal to 1 for different solution. So this is a technical 2. The technical which inspired us the most was proposed by Professor Andrew Stewart. This kind of problem was doing this way. You have a non-Gaussian models, which is kind of gamma coming from a Poisson process. And I should say that you have a positive gamma plus and a negative power minus. And if this gamma take positive, the system was stable because you have a minus value here. But if you take a minus value here, the system was unstable. So you're always switching from stable part to non-stable part, and this kind of switch was controlled by a Poisson process. Now, the question was like this, because this is extremely non-Gaussian, so whether people can do this in a simple way that approximates this non-Gaussianness by some Gaussian model or some simple non-Gaussian model. And the easiest one is to say that I ignore this stochastic background of this gamma bar. I just use a constant to approximate this original system. On the other hand, you can say that now assume my gamma was switching from positive to negative, never mind. I just ignore this Poissonness. I will say that this gamma was Gaussian, and the non-Gaussianness was appear when you multiply this gamma hat with u hat here. Then whether it is possible to say that I fit my two models to the original model and try to find the best constant that fits all these non-Gaussianness here. So in this case, we will try to identify or to approximate this kind of V mu sigma here for the expectation and the variance at certain time t. So if you see that we try to do approximation something from the linear stochastic differential equation, and all the message that we can have is mostly the PDF. For this issue and all this issue, that you try to use this probability density function, the mean and the variance, to approximate these unknowns. Then we will try to do something different, or to do something more like naive compared with the existing result. And we will do it this way. So firstly is a parameter identification by direct observation. And we will start with the simplest case of Ockelstam's Uhlenbach process. As we have shown before, that you have this direct problem with gamma, V hat, and sigma. You have initial state of V0 coming from certain random Gaussian prior. Then the problem that identifies these unknowns gamma, V hat, and sigma by the asymptotic behavior of Vt. And we also listened to the talk in the morning, second one, for this online regularization, but in my case, it was offline. So we tried to identify the parameter, but it was offline technique. Let's see. We have 3 unknowns. So in this case, you have to find out 3 equations or 3 parameters that you can obtain. Then let's take a look about what we can have. Of course, this is the easiest way that you solve this equation. And I should say that the main technique that I used here was isometric. That this is the field technique that you can use in the stochastic differential equation. We write down the pathwise solution here, and you will see that these unknowns appear here, 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 and here, and here. Now, I should say that the initial state was not important, because if the time t is large enough, this term will vanish. So that is why when I was reconstruct something or reconstruct these unknowns, the initial state was not important at all, because it will decay exponentially, especially assume that this gamma was larger than 0. So the hidden information was in this term and this term. Then what we can have? We know that if you have linear stochastic differential equation, everything was linear and everything is Gaussian. And the message or the Gaussian statistic that you can have is the mean and the variance at a certain time here. And you can see that both of these initial state will vanish at the same time as t goes to infinity. So this part was not important, but here and here was important. But you have 3 unknowns. If you only use the PDF, you have mean and variance, then you don't have enough information to identify 3 unknowns. So you have to have another one. And this kind of third condition was appear as a covariance. So if you see that, we try to see that what is the covariance starting from time t and the signal for the t plus tau. So which tells us that the connection between 2 signals at time t and t plus tau. And you will see that this covariance was depending on this variance of t and also a latent time of this exponential form. So can we simplify this one? And in this case, we have to define a new definition of this kind of so-called decorrelation time, which tells you that your signal starting from time t, it has certain memory after some time, but after some time, this kind of memory always disappear. And this kind of decorrelation time was built up from this autocorrelation function, which is just the covariance divided by the variance at time t. Then in this case, you will see that we remove the influence of the variance and we only obtain an unknowns depending on this gamma. And because all these parameters are constant, then this decorrelation time was asymptotically, it's just a constant. So we collect all these Gaussian statistics from the pathwise solution. You have the mean and variance and the decorrelation time, and you have only 3 unknowns. These 3 unknowns appear as the mean, variance here, this is a volatility, as well as the damping constant of gamma. So you have enough information coming from Gaussian statistics to identify these 3 unknowns. Well, the parameter identification that we propose here was not the same as people always do, in that you fit the path of your solution. We just ignore the path. We retrieve the information from the path to say that if we can estimate the empirical mean, the empirical variance, and the empirical decorrelation time, then we are good enough to identify all these 3 parameters shown in this OU system. And of course, you have a non-negative constraint, say that this gamma should be always positive, this sigma squared should always be positive, but it's not a big issue. So you have this minimization, which is, from my viewpoint, is rather new, because when we do dealing inverse problem, we always say that you try to approximate the path or the measurements that you have. But for us here, we have the path information, but we just retrieve certain information from the path instead of to fit the whole path itself. The final question is, can you estimate the empirical value? And I think that this is the easiest way that people can do when even you are a bachelor student, because you have the measurement of your VOTI, which tells you that this path will decay fastly, and it will reach some asymptotic point, asymptotic value, and it will oscillate because of the noise coming from this Brownian motion. So we will collect the data after a burn-in period. Then in this case, you just generate the mean from your measurement of V. So this is the easiest way that you generate a mean of your data. And of course, we also calculate the variance through non-biased estimation of this variance. Then you have the mean and the variance automatically from the data that you can measure. And to obtain this decorrelation time, you have to calculate the autocorrelation function, but we are lucky that in MATLAB you have this autocorrelation function tells you that what is the autocorrelation between different signals, and what you need to do is just to summarize all this data, multiply by the time step, because this decorrelation time, its own definition was integration for the autocorrelation function here. So I will show the numerical test later on, so I will not go into details here. Now, this kind of approach that we propose here, you try to identify by fitting the Gaussian statistics instead of the whole path, can be say that works well for the constant parameter. Then a natural question is, what kind of extension that you can take coming from this kind of idea to fit all these Gaussian statistics? And the easiest way is that, can you do the Langevin equation? Then all these functions, all these unknowns have become, say, functions. And of course, because you need to asymptotically measure the Gaussian statistics, and in this case, the function gamma, v hat, and sigma cannot be arbitrary. So we have to assume that at least they are periodic. And of course, for sake of simplest way that to explain all these things, I assume that the gamma, v hat, and the sigma have the same period. But it doesn't matter that if they are not the same period, we can still working on this. And we take the same idea that we proposed in a previous set, and we will say that what is the Gaussian statistics for this pathwise solution? We can write down immediately. But now this gamma, v hat, and sigma are function, so it's become a little bit complex, and this isometric become also complex. But nevertheless, we can do this, and we can also define so-called pointwise decorrelation time. Since you have the periodic function here, then the decorrelation time was also changed for the different time. Then a natural question is, if all these parameters gamma, v hat, and sigma are periodic function, can your signal also have this periodical structure? The answer is no, because the initial state will influence your measurement, but remember the initial state will decay exponentially, so this kind of influence will decay also asymptotically. Then we can summarize everything into this theory. So when you have this Langevin equation, and you assume that all these parameters gamma, v hat, and the sigma are periodic function of the same period t, and of course you have to assume that this gamma t in the same period was always larger than 0, because the system itself should be stable. Otherwise, it will explode exponentially. So in this case, if this t equals to kt plus zeta, then this t tells me that the large t is the period. So in this case, you take segment from the signal, say you take it segment by segment with respect to the time step of t, so that you generate different segments of your data. Luckily, if k goes to infinity, then this kind of asymptotic behavior for the expectation mean, mean and variance and the decorrelation time, they are also periodic. Which tells me that if you ignore this influence of the initial state, then you really have a periodical structure. But the payment is like this. You have a discontinuous kernel for your Freund-Holland equation of the first kind. And I can explain easily that in this way. That for instance, you take a t equals to k plus t plus zeta, then you can take some extra information tells you that from zeta, you can always take it from 0 to t to large t. Then you take some additional information from this zeta to large t to compensate the lossy information that you have measured here. But this kind of lossy information will appear as a discontinuous kernel here. And for the decorrelation time, if you define a new function with respect to this solution of 0 to zeta with respect to this gamma, then you can show that to identify this gamma, you just solve a Volterra equation, which that Professor Prato has mentioned this morning. I should also mention that if you see the equation here, the decorrelation time only depending on this gamma. The mean of your equation was depending on this gamma as well as this v hat appearing as the mean or as a force constant or force function appear in my Langevin equation. It did not show up for this gamma when you have this OU system because this kind of gamma, if it is constant, then it will disappear immediately. But if you have a general Langevin equation, this kind of gamma will influence when you identify this v hat here. And of course, if you identify this sigma square, you also have the same problem that you have to know the gamma first. So the minimization approach that I have before have to change a little bit. The kind of change was doing this way. So firstly, starting from this empirical decorrelation time, you try to identify the gamma first. When you have this gamma, then you can use this gamma to identify this v hat and the sigma square so that this kind of optimization approach was satisfied. I will not go into detail how we obtain the minimizer. I just mentioned that you have certain constraints to say that the sigma square should be larger than 0 because it's the covariance, it's the variance. And the gamma zeta should have the constraint that it's always larger than 0 if you integral it from 0 to large t. But if you ignore all these kind of numerical scheme, this kind of approach should be working quite well, that as we have known from different technical books for the regulation theory. So we stop a little bit here. So for instance, like if you see that everything is the function, then you have to solve certain integral equation which is appear naturally when you take this ODE system. The next question will be, can we do further? Or from the direct observation, can we go to more further aspect? And this brings us to the indirect observation. For instance, like we have a couple system. The first one was the unknowns. We have certain unknowns in this equation of this V, gamma V, gamma V hat, and sigma V, which is unknown to us. But we cannot measure the V directly. What we can measure is through another system, and this system was called U. And of course, we try to do everything which is like Gaussian. Then in this case, this whole system was Gaussian, that we take say multiplication, not multiplication, just additive model that say that this V was appearing as a false term. And it can be positive or negative according to the asymptotic behavior that you can have from this V. The question is like this. Can you identify the parameter in this system from only the measurement of this U? This is natural. For instance, like in the real situation, when you're dealing with data assimilation of atomic size, you have certain regime that's hidden from the measurements that you can have, tells you that it will switch from different states to perform like El Nino or La Nina, like in this atmosphere science. It will have the negative temperature or positive temperature in the surface sea temperature. And in this case, this kind of switching of this regime was unobservable. You cannot see the switch at all. But you can measure some data to try to recover or parameter identify these kind of unknowns here. Then this can be seen as an attempt to do such kind of research. Then our question was very natural. Can you, starting from the pathwise solution, can you identify this gamma V, V hat, and sigma V from the measurement of this U? And we have to assume that this gamma U and sigma U was known to us, because otherwise you don't have uniqueness. You only have the measurement of this U, and you only have 3 Gaussian statistics, but you have 5 unknowns, and it is impossible to identify them uniquely. So in this case, we will always assume that this U and the sigma U was known to us. So this is the pathwise solution, and you will see that this Vs was appearing here. So you have to put this Vt into this Vs and calculate the Gaussian statistics for this Ut. And of course, it is complex. But if you are dealing with all these constant value, things are simple, because you can calculate the expectation of this U, which is depending on this V hat appear as the unknown in this V, and also depending on this gamma U here. But I assume that the gamma U was known to me, because otherwise I don't have uniqueness. And also for the variance of U, it was depending on this sigma V, sigma U, and all these 2 damping parameters of gamma V and gamma U here. And of course, the decorrelation time of this U should and must, depending on this gamma U and gamma V, as well as you have to use this U hat here as the variance here. So we can show that as t time goes to infinity, if you have a couple system here, if you additionally assume this gamma U and the sigma U was known to you, then you can uniquely identify this gamma V, V hat, and sigma V. What happens if they are periodic function? We have succeeded in the Langevin equation by direct observation. Then the question is, can you do this if all these functions are periodic? Of course, it's very complex. So firstly, you have indirect observation, which tells you that you have to integration with respect to U at least 2 times. That is why we will have this double Fresnel-Holland integral equation. Your unknowns was appear here as V hat, but this kind of kernel was depending on this gamma U and gamma V, and this K was the discontinuous kernel that I defined before. For variance, it's even harder. You have 3, say, triple Fresnel-Holland integration of the first kind. Then your unknown was sigma V here, and also you have sigma U here. You just ignore this one because this is known. But you have to know this gamma v first. In both cases, you have to know this gamma v first so that you can obtain certain reconstruction of this v hat and the sigma v square. But for this gamma v here, this is even more complex than we have. So firstly, this gamma v was hidden in this p here. We defined a new function of p here, and this p was appearing into this this is actually a Fernholder intuition of the first kind. Then you have to do a lot of technique, I just omit detail here, to transfer the kind of decretion time with respect to this gamma v into a Volterra equation, but you have to dealing with the data calibrated more carefully, because it is really that you have to, starting from the decretion time, you have to do certain transformation of variables so that all this information can appear to identify this gamma v here. I just skip all these detail. Now let's take a look about the reconstruction. So we have the direct observation of this v, and we try to identify this gamma, v hat, and the sigma here. And we take a simple form of this gamma, sigma, and the v hat here. And of course, this is the reconstruction if you have m goes to 10 power minus 7. I ignore all these constant tests because they look quite good. So we're dealing with all this functional sense. This is doing this way. We take the period t equals to 1, then we generate all this observation for 10 power minus 7, because you have to have a lot of measurements so that the law of large number will give you numerically the empirical mean and variance and decretion time accurate enough. And the burning time was like 3/4 of your measurement, so you only take 1/4 of your measurement to generate the mean and variance and decretion time. And this is the damping parameter. The red one was exact function. The blue dashed line was the reconstruction, and it looked like quite good. But on the boundary side, we always have some problem. Then this is the sigma square. Remember, the sigma square should be always larger than 0. Then we have certain constraint here to allow you always have positive reconstruction. The worst part coming from the means, or the false part here. We always have some oscillation, and you can improve it if you increase the measurement. And I will show that evolution of the accuracy. For instance, like you're starting from the measurement of 10 power minus 5, 10 minus 6, 10 minus 7, and the law of larger number tells you that the more information you have, or the more measurement you have, the more accurate the mean variance and the decretion time that you can generate from the empirical value. And you can see that it's really improved starting from 10 minus 5 to 10 minus 7. And if you go to 10 minus 7, it's already accurate enough. And of course, for indirect observation, things will become also good, but we have to increase the observation from 10 power minus 7 to 4 times of this one. So in this case, you have quite accurate reconstruction of this damping parameter, force parameter, and the volatility parameter, and we still have the same problem here. I also show that this is the hat function here, v hat here, and we try to see that how it will evaluate with different measurements. So starting from 10 minus 5, or 4 times 10 minus 5, 10 minus 6, and 10 minus 7. And if you see that it will improve slightly from 10 minus 5 to 10 minus 6, but it will improve quite essentially if you go to 10 minus 7. But good way is that we can always measure or identify these unknowns from the indirect observation. And the more information you have, the more measurement you have, the better reconstruction that you can take. So finally, conclusions. So we try to propose a parameter identification of indirectly observed Uhlenbach process and Langevin equation, and we try to do it in a Gaussian statistics, which means that you fit the unknowns with the Gaussian statistics of your measurement instead of the path itself, because the path was really long. It's impossible to calculate this one. The future work was, say, firstly, what we have done was only Gaussian. Then what happens if you have non-Gaussianness? And this kind of non-Gaussianness will really, say, destroy all this structure here, and you can even go to higher moments like Knuth or different one, the third moment, fourth moment, as you like. But it will become much more complex than we have expected. And of course, can you do in some conditional Gaussian framework? And I will explain in the next slide. And what we have done was only one-dimensional stochastic differential equation. Can you extend it to high-dimensional? And we are highly promoted by the data assimilation technique. Then in this case, whether this kind of method can be applied into data assimilation was also intervened. And let's go to the conditional Gaussian statistics. We tried to do the stochastic parameter estimation of common filter proposed by Professor Andrew Maida from Courant Institute. They tried to say we have 3 random variables. All of them was controlled by different Brown emotion. Then you can measure this U, and there's 2 hidden Markov chain here, B and gamma here. Both of B and gamma was Gaussian, but you have non-Gaussianness of this U. Can you identify these unknowns in B and gamma? It is non-Gaussian for U, but if this U was known, the posterior of this B and gamma was Gaussian. So the overall PDF was non-Gaussian, but if this U was known, you take a segment along different time with respect to this U, and you will always have this Gaussianness of your posterior distribution. Then whether this kind of conditional Gaussian will help you to improve something, it will be very interesting. So I think that my talk was almost over, and I will try to, no, not yet, spend several minutes to explain why I'm here. So I should thank Ben that I was really appreciate or benefit a lot from the sequence of this Chemnitz Symposium on inverse problem. And this is the first time I participate in this Chemnitz Symposium, and I'm really happy to see that Antonio, you are there, and Barbara, you're here. So I'm the only final people in the behind. It was when I was a student, so this is the first time I participate in the Chemnitz Symposium on inverse problem. And after that, I have taken like 6 of them of this sequence. And I was proud to say that I have participated all of these Chemnitz Symposium on tour outside of Germany. I did not in Berlin last year, but I was participate all of these kind of on tour activity. And I really thanks Ben for all this effort for this. And I think my talk will stop here, and thank you for attention. Thank you.